Reduced row echelon form. A matrix is in reduced row echelon form if it satisfies the following three conditions. 1. The matrix is in row echelon form. 2. The leading entry in each non-zero row is 1. And 3. Each leading one is the only non-zero entry in its column. Let's look at some examples. Here we have a matrix that is in row echelon form, but not reduced row echelon form. The leading entries are 2 and 3, and not 1. So condition 2 is being violated. We can write an equivalent matrix, which is in reduced row echelon form, by scaling the two rows. Starting with the first row, we'll go ahead and multiply it by a half, and we have that 1/2 times 2 is 1, 1/2 times 0 is 0, and 1/2 times 8 is 4. We now have a leading entry of 1 in the first row. To get a leading entry of 1 in the second row, we're going to scale by multiplying by 1/3. 1/3 of 0 is 0, 1/3 of 3 is 1, and 1/3 of 9 is 3. We now have a matrix that is in reduced row echelon form. We see that the leading entries are all 1, and above and below, those leading entries are only zeros. Let's write out the corresponding system of equations. The first row gives us 1x plus 0y equals 4, and the second row gives us 0x plus 1y equals 3. This is equivalent to x equals 4, y equals 3. Notice that in this case, we got a unique solution to the corresponding system of equations, and whenever that happens, the right-hand side of the reduced matrix actually tells us the answer. Notice the 4 and the 3 on the right-hand side of that matrix corresponds to the solution of x equals 4, y equals 3. Let's look at another example. Here we have a matrix that is in row echelon form, but it's not reduced. First of all, we have a leading entry of 2 here, and we can fix that by scaling. We'll multiply that second row by a half to get 0, 1, 3. I also just rewrote the first row because we weren't doing anything to that row in this step. Notice that the leading entry in the second row is now 1. Condition 2 of being reduced is now satisfied, but above that 1, there's still a 4. In order to be reduced, we have to change that 4 to a 0. We can do that with a row replacement operation. We'll do row 1 minus 4 row 2. We start by just rewriting the second row because that row is not changing. And now let's go ahead and do the first row column by column. We have 1 minus 4 times 0 equals 1, and we place that as the first entry of that first row. For the second column, we have 4 minus 4 times 1 is 4 minus 4, which is 0. And we go ahead and put that as the second entry of the first row. And for the third column, we have 5 minus 4 times 3 equals 5 minus 12, which is negative 7. And we go ahead and pop that into the third entry in the row. This corresponds to the solution, x equals negative 7, y equals 3. Another example. Here we have a matrix which is already in reduced row echelon form. There's only one leading entry here. In the first row, it's the number 1 there, and below it is already a 0. Here's the corresponding system of equations, x plus 2y plus 3z equals 4, and 0 equals 0. Once again, 0 equals 0, although true, provides no useful information, so we can disregard it. For that first equation, we want to solve for the basic variable. In this case, the basic variable would be x, because x corresponds to the first column, and that's the only column with a leading entry. Y and z are free variables because the second and third columns do not have leading entries. So we go ahead and solve for x, giving us the general solution, x equals 4 minus 2y minus 3z, where y and z are free. Let's do another example. Here we have a matrix which is in row echelon form, but it's certainly not reduced. The leading entries are 1, 2, and 3, and above those second two leading entries of 2 and 3, we have some non-zero numbers. This time, let's go ahead and make those non-zero numbers above the leading entries into zeros, starting with column 2. Now, we have a couple of options for the row replacement operation we're going to use here. We could do row 1 minus 1/2 row 2, or we could do 2 row 1 minus row 2. These are the two simplest options. Let's look at this in more detail. The first row is the row that we're going to be changing, and the second row is called the pivot row because it's the row that has the pivot of 2. The pivot row never changes. We're going to write down the row that's changing followed by the pivot row. We always write the row that's changing first, that's row 1 in this case, and the pivot row second, that's row 2. And we always write this next to the row that's changing. In this case, row 1 is the row that's changing. Next, we can either multiply row 2 by 1/2 or row 1 by 2. Both of these will make the entries match up so that it's easy to cancel them. In the case of multiplying row 2 by 1/2, both entries will match up as 1. And if we multiply row 1 by 2, both entries will match up as 2. I'm going to use 2 because that will avoid having to do computations with messy fractions. Okay, now that they're matched up, we need to either put a plus or a minus sign between those two terms. We're going to use a minus sign in this case because 2 minus 2 is 0. In general, we use a minus sign if both of the signs are the same, and we use a plus sign if the two signs are different. In this case, the 1 and 2 have the same sign, so we use a subtraction. Okay, we begin by first rewriting the pivot row. The pivot row never changes during a row replacement operation. So by writing it down right away, you won't accidentally make a mistake of trying to alter it. Let's go ahead and column by column fill in the entries in the first row. We have 2 times 1 minus 0 is 2. 2 times 1 minus 2 is 0. 2 times 1 minus 5 is 2 minus 5, which is negative 3. 2 times 2 minus 8 is 4 minus 8, which is negative 4. We could also just throw in that third row because at this point in time we're not changing that. There's already a 0 in that row below the leading entry. Now let's take a look at the next leading entry of 3, and we have to get zeros above that leading entry. Row 3 in this case is now the pivot row. So we're going to go ahead and just rewrite the pivot row. Once again, during row replacement, pivot rows do not change. For the first row, we're going to be changing first row. Row 3 is the pivot row. They're already matched up. One's negative 3 and one's positive 3. So to cancel them, we just add them. Let's do this column by column. 2 plus 0 is 2. 0 plus 0 is 0. Negative 3 plus 3 is 0. And negative 4 plus 12 is 8. For the second row, we're changing row 2. Row 3 is the pivot row. We multiply row 2 by 3 and row 3 by 5 to make them match up at 15 and subtract to cancel. For the first column, we have 3 times 0 minus 5 times 0 is 0. 3 times 2 minus 5 times 0 is 6. 3 times 5 minus 5 times 3 is 0. 3 times 8 minus 5 times 12 is 24 minus 60, which is negative 36. Okay, we now have zeros in all the appropriate positions. We're going to go ahead and finish by scaling the 3 rows to get those leading entries to be 1. We multiply the first row by 1/2 to get 1, 0, 0, 4. The second row we multiply by 1/6 to get 0, 1, 0, negative 6. And we multiply the third row by 1/3 to get 0, 0, 1, 4. So the solution is x equals 4, y equals negative 6, z equals 4. Let's do one more example. Here we have a matrix in row echelon form, but not reduced row echelon form. We see the leading entries here are 1s going from left to right as we go down the rows. But above the second two 1s, we have some entries which are not 0, in particular that 2 and that 5. Let's look at column 3 first. We're going to change row 1. Row 2 is the pivot row. We multiply row 2 by 2 to make them match up and subtract to get a 0. Rewrite the pivot row because that's not changing. And let's go ahead column by column to fill in row 1. We have 1 minus 2 times 0 is 1. Again, 1 minus 2 times 0 is 1. 2 minus 2 times 1 is 0. 4 minus 2 times 2 is 0. 5 minus 2 times 0 is 5. And 7 minus 2 times 1 is 7 minus 2, which is 5. And we'll just fill in those last two rows because, again, we already have zeros in the appropriate positions, so we don't need to change those. Let's look at the fifth column now. We have to get rid of that 5. So we're going to change row 1. Row 3 is the pivot row. We multiply that pivot row by 5 to make them match up and subtract to cancel. These computations are pretty easy, so I'll just fill in the matrix right away. Notice that the 5 that's circled in blue becomes a 0 because 5 minus 5 is 0. And let's just do that last column in detail. That's the only one that involves any kind of computation. We have 5 minus 5 times 3 is 5 minus 15, which is negative 10. Let's write out the corresponding system of equations. Notice that each column corresponds to a variable. Let's call them x1 through x5, so that the first row becomes x1 plus x2 equals negative 10. The second row becomes x3 plus 2x4 equals 1, and the third row becomes x5 equals 3. We don't need to write down that last row because it's just 0 equals 0, which provides no useful information. I'm going to go ahead and solve for the basic variables, which are x1, x3, and x5. So x1 is negative 10 minus x2, x3 is 1 minus 2x4, and x5 is 3. x2 and x4 are the free variables because columns 2 and 4 do not have any pivots.